Hello, everyone. Well, welcome to Convex optimization lectures. So this is our 18th lecture, the last but one lecture of the quarter. Looks like we have a fewer than usual number of participants, but the numbers are still climbing. So we'll start slowly, and then hopefully by the time we get to the today's lecture on ADMM algorithms and more people will show up. Okay, so the plan today is to finish the last lecture, which I still have a couple of slides that I think is that I think are important to cover for you guys to have a more like holistic view of the field and the research front before moving towards other topics. All right. So this is where we stopped last time. We talked about the algorithm called SVRG, stochastic variance reduced gradient methods. And this is one of the many methods nowadays that deals with stochastic gradient descent for finite sum problems, which achieves faster convergence. So in particular, in this case, if you assume that the objective function value, the sum of fi obeys strong convexity, then you are able to use this algorithm and then get essentially the linear convergence while spending only one on the order of one stochastic gradient evaluation in every iteration. Okay, so that's pretty great, and we managed to went over the convergence analysis for SVRG, which honestly is not that difficult. So there are some corrections from the presentation last time that's added to the shared written notes that I've put on the course website, and I've talked about the changes and the small correction in terms of how we are making use of strong convexity like on Piazza. So if that concerned you, please go and look at the updated notes. So, but by the way, the notes that were updated, like there isn't a version of the wrong notes that were uploaded to the course website. So suppose you download that after the lecture, and that's the right version. Okay. So we talked about convergence, so what's more? So now we can get linear convergence, but in the batch setting, without the stochastic sampling of the gradient, we can also get acceleration. We can get faster dependence, better dependence in the condition number L over M. Can we get the same in the finite sum setting? So it turns out that we can, but there are some caveats. So specifically acceleration, like there are many versions of acceleration and algorithms that achieves these accelerated rates nowadays by various authors. So what you can achieve instead of having a clean cut square root of L over M, so the size of the data set creeps in interesting ways. So you are able to get the square root of dependence on L over M, but provided that you introduce another factor of N. And this term cannot really be improved. Okay, so this is a lower bound that applies to any methods, and there are methods that achieves this iteration complexity lower bound for the finite sum problem. Okay, so a lot of this acceleration tools for these fast gradient methods stay more or less on the theoretical level. So in practice, like we talked about earlier, if you add warm start to the problem itself, like doing acceleration may or may not be useful. Acceleration typically requires more careful choice of the hyperparameters, learning rates, and so on, and knowledge about the underlying problem, specifically what the number L and M are, and then your choice of sequences of learning rate and maybe the momentum factor would end up depending on those unknown parameters. Okay, so so we've already talked about momentum. So Nesterov acceleration can be thought of as as a momentum algorithm with a carefully chosen momentum factor. So momentum is like just another way of saying that you are making making use of more information from the past, and then like the previous iteration gives you some additional push towards what you're gonna move to the future. So instead of just moving towards the gradient direction, you also take previous iterations and then interpolate based on that. And since the previous iteration based on even earlier gradient calculations, so you can rewrite this as you can rewrite the entire update as a slightly different linear combinations of all the gradient in the past. So that's momentum. So so momentum can give you acceleration in convex optimization setting. What really makes the idea of momentum taking off is that it actually helps these algorithms to perform significantly better and converge significantly faster in non-convex problems, in particular in training deep neural networks. So that's quite mysterious why it is the case, because in general for non-convex problems, momentum like there are methods that you can guarantee convergence for momentum based like heavy ball algorithms, but like you don't really see an improvement from the convergence bound. But the improvement is there in practice. So there are gonna be other kind of explanations why momentum is useful in non-convex optimization problems or in large family of neural network training problems. Okay, so if we compare, say the naive heavy ball algorithm with Nesterov with a more formal Nesterov acceleration, well, you can see that they so this got applied to a convex optimization problem. You can see that they converge like with roughly the same rates, where the Nesterov acceleration the Nesterov acceleration works a little bit better in terms of not suffering too much from this ripple effect. But if you just draw the line for linear convergence, you can see that both lines are parallel to each other. Therefore, like from the theoretical perspective, they are achieving the same rate. Okay. Okay. So another line of work that aims at improving the stochastic optimization-based methods, stochastic gradient methods, stochastic first-order methods, are moving towards a complementary direction. So far we've talked about convergence rates. We've talked about how do we leverage the finite sum structure to yield a faster convergence rate for this more specialized set of problems. There's another family that aims at somehow, in some sense, finding adaptive step sizes that differs at different coordinates. Okay, so take this logistic regression problem as an example, and suppose we want to apply this logistic regression to say like a sentiment classification problem. Okay, so you got movie reviews, so you want to design a machine to read these movie reviews and then tell you whether this is positive or negative. Okay, so machines can read a lot faster, processing the text a lot faster. Therefore, like it might be able to give you a summary of a huge corpus that you won't be able to digest as a human being, even if like the predictions might not be always accurate. Okay. So in this case, a standard feature that people use is a kind of so-called bag of words feature, which essentially enumerates all the unique words, count its frequency from the sentence, and then like come up with this frequency vector to represent every sentence or every paragraph. So in this case, there will be like one on the coordinates indexed by subtle art. There might be something indexed by a masterpiece. So each one of these will be a one coordinate in this extremely high dimensional vector representation of this paragraph. Okay. However, if you do it naively without dropping out the so-called stock words, like for things like those that are uninformative about the sentiment, like maybe, like of, like the, and all the other words that occur significantly more frequently in all I guess in all paragraphs, then features with respect to those those columns will end up having a more significant effect in the learned logistic regression. Okay, so essentially you're weighting those features a lot more than those rare features, and the rare features can get more easily for those that are like very informative, like subtle arts and masterpiece. Those would happen much more rare, but like if not taken care of carefully, you will end up getting an algorithm that doesn't weight enough on this words that appear only in the tails of the distribution. Okay, so but as from a learning point of view, we want to come up with algorithms that are general, and we don't have to do a lot of feature engineering. So of course you can do feature engineering and use TF-IDF and use other like information retrieval techniques to create more informative features so that the standard logistic regression will just work out of the box. But ideally, maybe that doing that kind of hand-tuned feature engineering is not as good as having the algorithm to somehow learn a weighting function automatically, or somehow adaptively adjust the gradient such that we move towards a direction we move for longer step sizes on those coordinates that correspond to these more informative words, rather than comparing to other words like for and for maybe we want to design algorithms with step sizes that are much smaller on those uninformative features. Okay, so so consider the logistic loss. So this will be like the 0, 1 label version of the logistic loss, and then calculate the gradient. And the gradient is proportional to the feature vector xi, and then it has exactly the same weights on every single one of the features. Okay. Like we talked about, this might not be good. So can we do better than this? And so hopefully we can improve the convergence of the algorithm. So essentially what this is saying is that the underlying geometry, if you view it as an ellipsoid, the underlying geometry of the energy landscape is like very much skewed towards like a much sparser set of coordinates. So if we can use optimization tools to algorithmically enforce that, and then learn the right reweighting functions, then the algorithm will be more well conditioned, and then you are making more progress with just every iteration. Okay, so that brings us to the idea of AdaGrad. So this is a particular version of the AdaGrad that that uses coordinate-wise scaling. There's there's another version of the AdaGrad that deal with like more general version of AdaGrad that deals with this gradient vector and alpha, and it rescales things according to h some kind of approximation of h inverse half. Okay, so that's another version of the that's another version of the AdaGrad. So AdaGrad was actually originally proposed as an online algorithm that competes against competes against the best regularization function. So remember we talked about follow the regularized leader. Okay, and we've seen that in follow the regularized leader, if we design this regularization function carefully, if we design this regularization function carefully, so that this is say one strongly convex with respect to certain norm, and then if this norm is chosen in a very informative way, then the follow the regularized leader will be then follow the regularized leader will be significantly improving the constant in the regret bound, right? So sometimes the improvement is exponential, so you go from square root of n to log n. But the issue is that, like, how do we know which regularization function to choose a priori? And like the AdaGrad is designed so that you can essentially compete against a family of choices of this regularization function that chooses its norm and that measures a strong convexity and Lipschitz gradient Lipschitz constant in specific norm. So for this case, you are competing against all such regularization function or distance metric in terms of in terms of a quadratic function, square root of x, where h is required to be diagonal. So AdaGrad is able to compete against the best diagonal rescaling of the gradient, and then end up getting the best regret bound with respect to that. And this more general version, which I think you can find in the Elad Hazan book, yeah, he's also an author. It competes with an arbitrary quadratic form. So in some sense, you are measuring the distance. You are competing against any Mahalanobis distance measure of the geometry, and then you don't have to specify that ahead of time. Okay, so so I'll leave more details to be read by you guys yourself, because this is AdaGrad is a masterpiece. Later extensions of AdaGrad really have made it like one of the most popular algorithms in training deep neural networks. So in particular, there are Adam, which make small adjustments to AdaGrad, make it more like it offers a more flexibility in tuning learning rate, and then it also adds this additional damping factor that avoids the cases when you are dividing something that's close to 0 and so on. So Adam is a pretty practical extension of AdaGrad that has now been almost always viewed as the default algorithm for training many types of neural networks, including primarily LSTM style sequence models. And the idea of adaptive gradient actually dates back to much earlier from the older neural network literature. So there's this RMS prop and also RProp that uses similar ideas to train the network. Okay, so so I wanted to draw another connection between AdaGrad and the algorithm and another algorithm that we've learned in the lecture before the last lecture on online Newton's method. So notice that in online Newton's method, the updated rule is that we are basically doing some kind of quasi-Newton approximation of the Hessian. And instead of having the 1 over square root of 2, so in that method, we are updating the coordinates we're updating the parameters by moving towards this direction, which is different from autograd, but quite similar. So the difference is whether you have a square root of 2 or not in the hashing. So as a matter of fact, so autograd construct this in the very similar way to the online Newton method, using up to this point, using the gradient transpose as you observe. Okay, so I'll leave more to be discovered and by yourself by reading the original autograph paper and or the textbook. So so here's how Atom works. So Atom adds momentum to both the estimate of the gradient and the estimate of the individual coordinate, estimate the scale, estimate of this diagonal approximation to this to the hashing. So using like just basically momentum update rule. So there are more hyperparameters, but if you get all these hyperparameters correct, and this will be a more powerful algorithm. And in addition, it adds this additional term for stability. Okay, so that's that's a simple change from autograph. And what we've seen is that which comes out of a very different context is that you can actually get more or less the same performance of Atom using a much simpler algorithm. So Science GD is what we propose, and in particular Science GD with momentum basically use the same definition of this. Basically use the same definition of this momentum by keeping track of this momentum factor. But instead of moving towards the momentum direction, you are rounding this momentum. If it is greater than 0, then you make it 1. If it is negative, you make it -1. So you basically take on a 1 bit. So the motivation here was from like compressing the optimization process so that we can do better distributed training, because the communication is sometimes a big issue and sometimes a bottleneck in distributed training of machine learning models. Therefore, like we wonder whether we can just get away with sending 1 bit per coordinate, which leads to 32 times savings of from representing a floating point number in full precision to representing just 1 bit. Okay, so this algorithm is very similar to Atom in the sense that both divide the momentum by the square root of the momentum calculation itself. The difference is that in Science GD, like we don't have to keep track of this V parameters in every iteration, and it's much simpler, and it's 1 bit. Okay, and also we have an interesting convergence analysis that relates to the steepest descent, and turns out that it was a very simple analysis, and that we can show that this algorithm actually works, and it sometimes working even better than the standard stochastic gradient descent. Okay, so in practice, when we compare Science GD with momentum, which is called Signum, with Atom, we see that like virtually they have the shapes of their optimization, the learning curve have no differences. And comparing to SGD, like it's a lot. Comparing to SGD, it's a lot faster in the beginning, and then it gets to a slightly worse bounds in the slightly worse bounds towards the end on the test accuracy, because SGD still generalizes best, but as an optimization algorithm, so we find a lot of correlation between Atom and Science GD. Okay, and for those who are interested, you can feel free to take a look at our paper from 2 years ago. Okay, so there are a lot of references and a lot of activities in optimization for machine learning and statistical purposes, and for large scale machine learning that interfaces with the system, with algorithm, and also with distributed computing. So so one recipe for getting your research done and finishing your thesis is to maybe like find a sweet spot that gets the benefit of optimization and a system performance at the same time, and that might be something that could be highly novel and will be picked up by people from your respective community. Okay, so here are the references for the finite sum, and here are the references for the adaptive gradient methods and other methods that analyze these stochastic gradient based methods very carefully. Okay, so let's move to our next topic today. So this is another family of algorithms in optimization that has been extremely popular, I think, since the 2009 and 2008, 2009, after Stephen Boyd have written that paper about ADMM. So that paper has really nothing new in it, because the techniques and the methods are all known, just with a different name. But like his paper served as a huge push of this idea, and then made it significantly more user-friendly for people who have working knowledge about convex optimization and are able to code up an algorithm, but not able to like analyze the convergence of an algorithm to actually pick up this idea and use it to solve their own problem. So at the end of the day, optimization becomes a language where you can dump your creativity to come up with interesting objective functions that you can minimize. And then once you have that, the ADMM is often the tool that you can make use of to come up with a very reasonable and fast algorithms for solving your objective function. So we'll see some examples in that front in today's lecture. So let's skip this. So before we start talking about algorithms, let's have a quick recap of a tool that we'll be using for deriving like those algorithms. So so I hope you still remember conjugates, the convex conjugates, Finchel conjugates, or conjugate functions. So the lectures from on duality was a couple of lectures before, and you've done the homework. So I hope like these concepts are still like not too foreign to you after a few weeks of working on something else. Okay, so let's go over this slide. So for any function f, we can define is convex conjugate or Finchel conjugate using this formula. Okay, so when this function f is also convex, then f and then f star's conjugate will give you back f. So from this definition itself, it also gives you the nice Finchel-Yang inequality, which holds for any x and y and for any conjugate pair f and f star. Okay, and well, suppose we take the argmax, or equivalently the argmin here. Okay, then we can substitute this into into the optimality equation of solving this Finchel solving this Finchel conjugates by its definition itself, and then get that and get that you have this nice symmetric relationship. Okay, so this basically says that the Finch's inequality takes equal if and only if x is a subgradient of f star at y, and y is a subgradient of f at x. Okay, so equivalently, so this can just directly follow from the definition of the Finch conjugate. And in addition, if f is strictly convex, then you know that the argmin is a singleton. Therefore, this particular argmin will give you the gradient, and then f star is differentiable. Okay, with this recap in mind, so let's move on to talk about the first algorithm that we'll talk about today. So the idea is that we're going to be slowly building towards ADMM and then talk about some of the predecessors of ADMM. Okay, great. So looks like we now have 20 plus people. You're not late, and yeah, things are getting more interesting today. So so let's start by talking about the algorithm dual ascent. Sometimes we like in the dual correspondence lecture, we talk about a lot of examples where it is useful to derive the dual Lagrange dual optimization problem or the Finch dual optimization problem, and then solve the dual instead of solving the primal. And suppose we can solve the dual and then use the KED condition to reconstruct the solution that we are looking for in the primal, and that will lead to a faster algorithm sometimes. And in particular, that's because sometimes the dual has structures that are not present for the primal. But what if we cannot actually derive the dual? So what if the dual, Lagrange dual, is not available in closed form, so we cannot directly optimize it? So in this case, we can still think about how we can solve the dual using the gradient-based methods, and then leverage the previous facts that we've talked about in the last slide, that essentially construct the gradient of the dual by solving by solving an optimization problem involving the primal. Okay, and if that's efficient, then you will be able to do that very quickly. So this is related to the SDCA stochastic dual coordinated ascent algorithm that we talked about in the last lecture. But this is a more basic batch version of that algorithm. Okay, but after this lecture, you can just pick up SDCA and then understand how it works relatively easily. So for concreteness, let's consider this equality constraint convex optimization problem where we just want to minimize objective function subject to a constraint. So in this case, then we can write down the dual problem as follows, right? So this involves just lifting this AX equal to B, write it as a Lagrange, write it as a Lagrangian form, and then solve for the Lagrangian by minimizing over X, and then express everything as a function of the dual variable. Okay, so. Okay, and this is equal to the minimum of X of this Lagrangian. Okay, and since this is equality constraint, we don't get additional constraints on this dual parameter U. So using the fact that this F star, the objective function involves a linear term in U and the conjugate of F, then we can I guess we can talk about we can calculate the gradient of this dual objective function, and then write it as follows, right? So just apply the subgradient calculus so that we get rid of this linear term, and then we get the gradient of this, and then apply the composition of the function with the affine transformation. We get this A subdifferential f star here. But this is something that we can calculate without knowing what f star is. This is something that we can calculate by solving a particular optimization problem in the primal, right? So we can simply solve this and then use a property in the first slides, and then substitute this argmin into this simple equation, evaluate the residual, and that gives us the residual of the slack, and that gives us a gradient on the dual. So the simple dual subgradient method would be adding, or will be keep adding this with some initial point to u0, and then you keep repeating this gradient ascent step. So since this is just a standard gradient ascent or gradient descent, if you minimize this g of u, then all the tools and all the techniques that we know about gradient descent would naturally apply here. So specifically, if the original function to minimize f is strictly convex, then we know that f star is differentiable, right? And then this becomes a gradient descent. If this is strongly convex, then can anyone guess if f is strongly convex, then what's the properties that we can say about f star? Anyone? Any takers? Okay, there's a guess says also strongly convex. Suppose f is like this convex, then like f star, like we don't know much. It's also just convex. I suppose f is strictly convex. Then f star is differentiable. Of course, the convex thing is still holds. The f star is differentiable, right? And suppose f is strongly convex, then of course f star is still convex and differentiable. But are there any additional properties? So the guess is strongly convex. But something stronger than differentiable would be to say the gradient is actually Lipschitz. So the natural implication of strong convexity is that f star is, say, strongly smooth, which says that it's not only differentiable. The gradient will change slowly as you change the input to the gradient. Okay, so this is this can be formalized in the following theorem on the duality between strong convexity and strong smoothness. So which says that for any function for any strongly convex function with parameter m, and then the gradient of its differential conjugate is Lipschitz with parameter 1/m. Therefore, if the strong convexity parameter gets larger, so that means that its differential conjugate is smoother, right? So and the analogy goes vice versa. Now that you consider f star star is also, it gives you back f, right? So suppose f star is strongly convex. If the dual is strongly convex, and the primal is strongly smooth or gradient Lipschitz. So this essentially is saying that strong convexity and smoothness, they are they are almost equivalent to each other. So if you have a problem that's strongly convex but not smooth, you can convert it into a problem that's smooth but not strongly convex, and then solve that problem, which you can apply techniques in gradient descent. Similarly, suppose you have a problem that's smooth but not strongly convex, you can convert it into the dual problem, which will be strongly convex but not necessarily smooth. So in that case, like if the online gradient descent based method works, then you'll end up getting the 1/t rates, just very much like the 1/t rates that you get for the differentiable and smooth functions. Okay, and hopefully you can also do acceleration. So a lot of these pictures are now much clearer than before. And using duality, so there are all combinations of algorithms that solves the primal and solves the dual and solves the primal and dual at the same time. So let's like spend 1 minute to prove one direction of this theorem, and then we'll leave the other direction of the theorem as an exercise, so that you can convince yourself that this is always the case. So recall the definition of the strong convex function G being stronger than the convex function. You can write when x is a minimizer. Okay, so in the case when x is a minimizer, then you can get rid of this linear term, because as a minimizer, you know that there is a subgradient that's you know that there's a subgradient that contains 0. Okay, so you can write this. Now using the let's define xu to be the gradient of f star of f conjugate at u, and xv to be the gradient of f conjugate at a different place. Now that we wanted to work out the Lipschitz property of this gradient of f star, so this is a natural thing to do. So we wanted to somehow bound the difference between these two using the differences of u and v, right? So suppose we write this, and now let's make use of the properties of strong convexity of f. Notice that notice that suppose this is strongly convex in x of v, then adding any linear function doesn't actually change the strong convexity, right? And also we know that xu is a and also we know that xu is a minimizer of the whole thing, using the fact that from the first slides on conjugate. So we know that xu actually minimizes okay. Therefore, we can just apply this rule and then write down this equation. So similarly, when we swap u and v, we can write the same equation by simply applying strong convexity. Now let's add things up. Let's add the two equations up, and on the right hand side, we'll get m xu minus xv square. And then if we move things around, so first of all this f would get canceled out, so we won't have any f. Let's move all the other things to the left hand side. So we will have u transpose xu minus xv, and then we'll have minus v transpose xu minus xv. If we collect everything together, we'll have u minus v transpose xu minus xv, and this is smaller than m xu minus xv squared. Okay, now let's apply Holder's inequality. Let's apply Cauchy-Schwarz, and then we get u minus v xu minus xv, and then this cancels with this square term, and we end up getting xu minus xv square smaller than 1 over m u minus v square. Okay, but xu and xv are just a gradient of the conjugates. So that implies the gradient of the conjugates minus gradient of conjugate v smaller than of m u and v. Right, so which checks the definition of this gradient of f star is Lipschitz with parameter 1 over m. Yeah, I'll leave the other direction of this equivalence as an exercise. Using this, we can see that, like, suppose f is strongly convex, then this dual gradient ascent algorithm will converge in terms of the suboptimality of the dual problem at a sublinear rate of 1 over k, or 1 over epsilon iteration complexity. And suppose f is simultaneously strongly convex and Lipschitz, gradient Lipschitz, then we know that f, the dual objective function is also simultaneously strongly convex and gradient Lipschitz. So using the relationships that we had previously, we know that this will be L tilde and this will be M tilde on the dual, and then we can derive a linear rate with this coefficients being 1 minus L tilde M tilde, right? Which is the same as I guess 1 minus is it yeah, let's see, 1 over L if you substitute M as 1 over L. Yeah. So in other words, like when you have linear convergence, even though you have swapped the strong convexity parameter and the strong smoothness parameter, and due to this reciprocal, the convergence rates that you will end up getting in the unaccelerated gradient descent will end up being the same linear convergence. Okay, so this is a nice application of something that we have learned before, and now by now hopefully you have internalized. So the motivation of doing like dual ascent algorithm is in fact the following. So this is one of the major motivating applications of designing the ADMM algorithm in the first place. Okay, so think about the following problem where the objective function is actually decomposable into blocks. Okay, so x separate coordinate wise into b blocks, and then maybe you're working with a like a supply chain problem where each one of these fi is something that depends only on the local on the local parameters of your factory. And then you have a global optimization problem to solve, subject to some kind of global planning constraints that allows you to that requires you to satisfy some regulations, restrictions, and to maybe to meet the demand globally. Okay, so this kind of problems are quite common in the operations research. And in this case, like the challenge of solving this optimization problem is actually completely coming from the constraints. Supposing that each one of these xi is a much lower dimensional problem, and then you can use things like a bisection and so on to solve each problem separately. If you do not have this equality constraints that the optimization is subject to, this will be a trivial problem to solve, where you can just solve this problem for every fi separately. Okay, so suppose we apply the dual ascent to this problem. notice that essentially in every iteration, we are only updating the dual parameter. But the construction of the gradient of the dual objective function requires us to solve a primal objective function of the following form. Right? Suppose we write the Lagrangian and then try to minimize the Lagrangian, and that problem decomposes into small chunks, and you can I guess each one of them you can make this xi, right? And that says that like if you want to run dual ascend on this problem, you can essentially calculate the gradient very efficiently and maybe in a distributed fashion. So the dual ascend in this setting have the system benefit of every individual node can just calculate their own calculate their own update of their chunk of the parameter for solving the first, and then communicate that to a centralized server, which collect all the gradients, collect all the information that are needed to calculate the gradient, and then like update the parameter, and then send the aggregated parameter back to every individual node. So this is a parameter server. This is a parameter server scheme that is like a useful abstraction of the distributed optimization problem, and you can think about it as just a simple MapReduce framework. Okay, like in practice, like the server might be multiple machines, and the different nodes might be multiple machines that are represented like in an abstract way, and maybe like they're all in the same machine where the server is the CPU, and every node is one unit in the GPU, one unit of the GPU, maybe one processor on the GPU, having their own memory and so on. And the communication channels are more complicated, but this remains a pretty useful abstraction to think about distributed optimization. Okay, so what happens is that this dual decomposability is completely induced by the structure of the problem and the way that we decide to solve this problem via dual ascend. So what if we have inequality constraints? So I argue that we can do the same for the inequality constraint, and with more or less no losses at all. Right? Suppose we replace this with an inequality constraint, and then we can construct the Lagrangian in the same way, and then since the potential conjugates is like a general statement, we can still calculate the gradient using the same way we calculated before, in the distributed fashion for every chunk separately. But once we have this, we move this towards a gradient direction, but that might lead to us getting out of the feasible region for you. So notice that the inequality constraint for due to the complementary slackness, and also due to the dual feasibility, you have this u that's larger than 0. But that's a trivial constraint that we can project to, right? So the solution is to simply involve clipping the updated solution to the non-negativity call, to the first arcent of the coordinate space. Okay, so there's an interesting interpretation of this algorithm from Vandenberg, which talks about the particular problem called price coordination. Like suppose this algorithm is a system and with many units, and each unit chooses its own decision variable xi. In particular, is xi might be how each unit allocates its resources. And well, but there are some global constraints on the shared resources that they all need to satisfy. That's in terms of the inequality constraints given here. Okay, so what's the implication? What's the meaning of this dual variable? So from say support vector machine, we've already seen that the dual variable can have very interesting meanings, and similarly in max flow min cut, and both the primal and dual variables have their associated meaning. So in this case, you can think about this dual updates as like subtracting the slack. So Sj are the slack, are like how much that you still have now that you can like on one particular resource that you can still increase the demand. You can still increase the expenditure on that particular coordinate. So if that happens, let's move towards that direction and make use of that available resources. And what this is saying is that the corresponding dual variables may represent the price of a particular resource represented in that coordinate. So moving towards the moving towards the slack direction. So notice that this S can be either negative or positive. Suppose the slack is positive, then that means that we're good. That means that we are not that means that with a current X, we're not actually like using up all the resources that's available. And suppose Sj is negative, then that means that we have already overutilized this particular resource. Therefore, let's increase the price to adjust for that, so people will end up using less. So think about this as a market where you automatically like set the price in the right way. So the gradient descent algorithm has this interpretation. And how about this projection step? The projection step ensures that after all the things that you do, the price should be non-negative. Right? You can have something that's zero, but having a negative price would mean like systematic failure on a lot of things, which you shouldn't really have. Okay. So the issue about dual ascent method is that it requires the function f to be minimized to satisfy like strong condition. So it needs to be strictly convex for the gradient to exist. Otherwise, you will suffer the subgradient stochastic subgradient descent or subgradient descent like slow rate of convergence. So people can now sort of a way that you can actually apply the same very similar algorithm but solve a much larger family of problems using something called the augmented Lagrangian method. So we'll talk about the augmented Lagrangian method before we go to our break, and then we'll come back and talk about ADMM. Okay. So the idea is that in the cases when f of x is not really strongly convex, can we make it strongly convex by solving an approximate problem? And then as we get closer to the optimal solution, we can change this this parameter rho, and we can decrease it so that we will end up getting something that's closer to the original problem. Okay, so this is the idea that we applied when talking about barrier methods for the interior point methods. So this is very similar, and also this is related to the smoothing idea in proximal gradient. So notice that in smoothing, we're making the objective function smooth. Using the by minimizing the Moho envelope instead, and and in augmented Lagrangian methods, we are making this problem strongly convex, and then solve this augmented Lagrangian problem instead, rather than the original Lagrangian problem. So the reason why it is augmented Lagrangian is because this is a Lagrangian. This is the augmented term that you add to this Lagrangian, which makes it more and more well behaved. Okay, so another thing is that just like the Mohl envelope that preserves the the objective the optimal objective function and the optimal objective function value, and the augmented Lagrangian also preserves the optimal solution, right? So notice that it's subject to AX equal to B. Therefore, at any feasible solution, this term needs to be 0. Okay. Okay. Now that with that, we can just apply the we can simply apply the dual ascent on this problem instead. So notice the connection of this to the proximal point algorithm, which aims at solving minimize any f of x that doesn't have a smoothness condition. Okay, so instead it minimizes the Mohl envelope of f of x that keeps running the prox operator, which correspond to doing gradient descent in a primal, and this corresponds to doing the gradient descent on the dual by adding this additional term to make sure that it is strongly convex rather than smooth. Okay, so in other words, the augmented Lagrangian method is dual to the proximal point method. So another thing is that this approach actually gives us a very natural choice of the learning rate that we can use in the dual. Notice that we've set the learning rate, so we don't have to tune the learning rate at all. So this is achieved because of the duality between strong convexity and strong smoothness. Because in the dual, when we have augmented the objective function, then the dual will necessarily satisfy the smoothness condition with parameter 1 over rho. Therefore, the natural fixed step size to choose for this would be 1 over L, which is rho. Okay. So this is coming from our gradient descent theory. Now, like, there's another interesting interpretation of why this rho is chosen to be why this learning is chosen to be rho. So let's consider the first order optimality condition for this for solving this augmented Lagrangian minimization problem. If we just take the sub differential of this and then use a composition rule, and then we end up getting this. So notice that if we take xk, notice that if we take the constructed xk, that's if we substitute this x to be the next iteration, then we'll naturally end up getting this equation, which directly corresponds to the first order optimality condition of the original problem, of the original problem without the augmented Lagrangian. Okay. So in practice, this algorithm converges a lot faster, but since the key motivation and application of doing all these is a decomposable f, so when you solve this problem instead, thanks to this term, then you no longer have the decomposability. And this is precisely due to the added augmented Lagrangian term. Okay, so we'll go to our break and come back at 2:12, and then we'll talk about how to resolve this problem using the alternating direction method of multiplier. Meanwhile, if you have questions, please post them in the group chat, and I'll respond to that after the break. Welcome back. It's 2:12. Let's resume the lecture. Are there any questions up to this point before I move forward? All right. So so far the story goes that we we are motivated to solve this decomposable optimization subject to constraints. And then a reasonable algorithm to solve that is to solve the gradient descent in the dual. So of course you can also do stochastic approximation by sampling the different blocks in which you get a stochastic gradient type algorithm in the dual, right? So which gives you something that's very similar to SDCA. I guess then these algorithms are quite unstable unless the function f satisfies some strong assumption in the f is smooth. But that can be resolved using the augmented Lagrangian methods by adding this additional regularization term to make it more well behaved. However, that breaks the decomposability in the first place, which defeats the purpose of studying these methods, at least in the original context in the first place. Okay, so now we get to a more general family of algorithms called alternating direction of method of multipliers. So so notice that they're alternating direction, but then there are also the method of multipliers. So method of multipliers is another way of saying the augmented Lagrange multiplier based methods. So therefore, you can think about this as an extension or a generalization of the original augmented Lagrangian base methods. So ADMM solves the following family of problem with two objective functions that's decomposable. So you want to simultaneously minimize fx plus gz subject to a linear equality constraints. Okay. So how do we derive this? As before, let's augment the objective by adding this Lagrange multiplier term, and then let's lift this constraint up into the Lagrangian, so we get the augmented Lagrangian. Okay, so this how this algorithm works follow a very easy mechanical calculation. So whenever you have a problem that can be formulated in this form, you can just derive the Lagrangian and add the augmented square term of the Lagrange multipliers to penalize the residual. And then it goes by simply iteratively repeat the following three steps. The first step would be take the augmented Lagrangian and then minimize that over this parameter x. The second step would be to fix this new x and substitute that into this this augmented Lagrangian, and then solve the argmean over the second group of parameter z. Okay, and once you get z, you substitute both x and x and zk, xk and zk into L, and then derive the gradient. So notice that this is the only term that involves u. So you can calculate the gradient to be simply the residual of your constraints. Then you move towards the direction that's given by the residual with a learning rate that's pre-specified here by rho. Okay, so three simple steps in every iteration, and each step depends on the update of the previous iteration. So you can think about this as some kind of block coordinate descent of this saddle function over x and z, and then you do one step of gradient ascent in the dual. Okay, so if you consider solving the same problem using the original Lagrange multiplier based methods, augmented Lagrange multiplier method, or the standard method of multipliers, so it will be more expensive, because then instead of minimizing this towards two alternating directions, so direction x and then direction z. In the standard method of multipliers or ALM, so what you need to do is to jointly minimize over x and z. and that's the reason why it breaks the decomposability. So even if f decomposes into x1 to xb, the Lagrange multipliers won't really decompose. However, in the ADMM updates, so we'll see from the examples that will come up, this actually is okay. So we still retain the like, so basically we can optimize over each block separately in the sequential way. So we're basically doing coordinate descents over each one of the blocks, and then based on the update, then we'll update the next one, and we do that in a cyclic coordinate descent manner. So at the moment we're just dealing with 2 blocks. All right. So the convergence analysis of the ADMM algorithm is a lot more difficult, mostly because this is not just a gradient descent method in the dual. So it updates the dual using gradient descent, but before the one step to the next, there are also a lot of updates in X, which doesn't really look like the same way that gives you the gradient gives you the gradient of the differential conjugate of the dual problem. Typical convergence analysis for ADMM are of the following form. So there are 3 types of convergence results. You can talk about the residual convergence in the sense that at the asymptote, when the number of iterations goes to infinity, you get a feasible solution. And then you also get the convergence of how the sum of the iterates f and g, this is a primal objective function, converges to the optimal primal objective functions. And in terms of the dual, you can show that this the dual would end up converging to the optimal solution. In terms of measured in terms of the first order stationarity condition. Okay, so notice that you don't actually get a convergence in terms of the duality gap, but there is a like a certain quantity that you can use as a surrogate of the duality gap to measure the convergence of ADMM. Fancier convergence analysis for ADMM has been still like an area of research. So there are a lot of papers about the linear convergence of ADMM under specialized conditions, but I think none of them are super general, and it took the researchers many years to generalize ADMM from just 2 blocks to multiple blocks. So here are some of the references about the convergence of ADMM that goes beyond the original asymptotic convergence, like in the older optimization literature. Okay, so let's take a look at the algorithm again, and then like maybe we can come up with an alternative a scaled form of ADMM that's more interpretable on the dual. Okay, so let's just do a trivial change by replacing the dual variable u, the Lagrange multiplier, with w, which is simply u divided by rho. So in this case, the update, in particular in the 3rd step, would involve no learning rates at all, and the learning rate is set to 1. Okay. And of course that needs to be taken back, and then when you replace that, when you rescale that rho in the original formulation, and then you get W without leading coefficients as well. Okay, so sometimes when people talk about ADMM and then write down the pseudocode block for ADMM, so this is often the algorithm that they are referring to, rather than referring to the original version when the dual variables are represented in the its-original scale. Okay, so there really isn't like too much computational benefits that comes out of the scaled form, except for this interpretation that the current iterate of this scaled dual variable w is simply the cumulative sum of all the residuals on the satisfiability of the linear equality constraints that you have experienced so far. Okay. So in the remainder of today's lecture, I'm going to focus on giving examples about ADMMs. And once we get some exposure on some classical examples of optimization problems that can be solved using ADMM, we'll talk about consensus ADMM, which is one way that you can always do distributed optimization. And then we'll also talk about special cases of ADMM where it leads to like highly practical algorithm where every iteration can be solved in linear time or even sublinear time. Okay. So to begin, recall that ADMM solves like this type of problem. But this type of problem, like with a general like ax just plus bz is equal to c, this type of problem. And a special case of that would be to simply take x to be equal to z so that we can decompose two objective functions f and g. So one of them might be smooth, the other might admit a fast prox operator. So in this case, when we do ADMM, when we write ADMM in this form, so also notice that this is also without lots of generality, because you can define this x tilde to be ax, and you can define z tilde to be c minus bz, in which case you can convert all problems that can be solved by ADMM into this seemingly more specialized form with a slightly different f and g. And since these are linear transformations, and all these conjugates like would so all these functions will not be too different from their original form. So suppose we solve the ADMM for this problem that are designed to simply split the two objective functions of the same objective variable, and then we end up getting update rules of such a form. Okay, so we'll have some examples of such cases where we need to do such a decomposition. But in this case, the ADMM steps are particularly easy because it can be written in terms of prox operators for both minimizations of the augmented Lagrangian. So it becomes just like projecting this term or solving the prox with respect to f, and then solve another prox with respect to g, and both having this t parameter set to be 1 over rho. So again, from our interpretation of the prox operator, so this can be thought of as a gradient descent on the smooth objective. Okay, so so this update rule is related to the older idea. So that's the reason why I said ADMM like was known a long time before it became popular. It's just known as a different name on called the Douglas-Rashford splitting method. Okay. So let's consider a few examples of this. So since we know that ADMM can be used to solve such composite optimization problem, let's apply it to lasso and see what kind of algorithms that we get. Okay, so so let's first rewrite this lasso problem by introducing this trivial equality constraint so that we can split the non-smooth L1 norm term with the square L2 loss function that's smooth. Okay, and then the ADMM step. So let's try deriving it. So we'll have the Lagrange multiplier equal to x theta plus lambda alpha 1, and then plus the U transpose theta minus alpha plus half rho beta minus alpha square, right? So this is the augmented Lagrangian depending on beta, alpha, and rho, and the dual variable u. Okay, so suppose we first optimize over beta. So the beta update would be, so notice that this term, this term, and this term depends on beta. So this is a quadratic minimization problem over beta where the closed form solution exists. And you can work it out by taking the gradient and set it to 0. And the update rule for beta simply involves solving a linear system of equation of the form that. But this is a ridge regression solution, right? So this is simply solving a ridge regression with a regularization parameter rho. And with this additional regularization rho, then the problem becomes well specified, and there are fast methods for solving this. There are fast methods for solving this in time that's proportional to you can solve this in time. NNZ of x transpose x, actually NNZ of x multiplied with log 1 over epsilon, maybe divided by rho, right? Yeah, if you have taken numerical linear algebra, so you will see that you can get this scaling using the conjugate gradient methods or preconditioned conjugate gradient methods, and sometimes you also actually get acceleration in which you get the square root of rho dependence here. Now the second update rule is to find, so alpha k is equal to arg mean of this L, beta, alpha, and u, when beta, alpha, and u are fixed. Okay, so if we look at it, so this becomes arg mean with this lambda a alpha plus the other two terms that both depend on alpha, but this is a quadratic function, and with an identity with an identity matrix in the middle, so you can rewrite this as alpha minus half rho alpha minus something, right? Alpha minus something that you want to start the prox operator from. And this is something that can be solved using simple subtracting with the coefficients when you divide both sides by rho. Okay, so that's probably another reason why you want to work with a scaled version of the ADMM algorithm, because then this becomes the subtracting without needing this additional rho. So the point is that this is something that can be solved in linear time as well. Like this one might not be linear, but this is the fastest that you can get, and people genuinely believe that the ridge regression problems are more easily solvable because this x transpose x in the low dimensional setting is d by d, right? So in the high dimensional setting, d by d is much larger than n by n, but in those cases, this problem is sparse. And then with this additional regularization, this problem can be solved very efficiently. And the third update is trivial. It's just adding the residual to the dual variable. Okay. In practice, when there are so many lasso solvers that has been proposed, if we compare them numerically on a toy scale problem with n equals to 200 and the dimension equals to 50, then we see that the really fast implementation, the Fortran implementation of those coordinate descent is still the preferred choice. ADMM is pretty comparable to all the other methods. Accelerated proximal gradient does reasonably well, but ADMM is not too far behind. Like it does depend on the choices of role. For some role, it performs better. For other role, not so much. But basically, the story is that it behaves more or less like a first order method. Okay, so considering, so at the end of the day, it's really a matter of how expensive and how cheap it is to complete every iteration. So yeah, there are also many other examples where ADM can be significantly faster than proximal gradient methods. In particular, for those cases where the proximal gradient method, when the problem is not well conditioned. Okay, so in practice, the choice of role can be somewhat delicate. So there are good heuristics that are available that's recommended in the papers about ADMM, but there isn't like a standard way of choosing this so that you can get the fastest convergence for all problems. In practice, what I like to do is to in some sense control this rho parameter by somehow looking at in every iteration what's the primal residual and the dual residual. If the primal residual is too small comparing to the dual residual and it's going to 0 at a faster rate, then I'll increase rho. If it is the other way around, I'll decrease rho. So it becomes a control system, and this was this is a strategy that's recommended in Boy's paper. Like basically double rho, like the moment you see some imbalanced decay of the primal and dual residual variable. So this procedure works quite well in practice in most cases, but sometimes it can get sensitive and not surprisingly, it doesn't enjoy the same convergence result of using a fixed rho. Okay, and also when applying ADMM to your problem, there are multiple different ways of deriving ADM. Sometimes these different forms of adding the dummy variables can make a difference on how efficiently your problem can be solved. Okay. Yeah, let's take a look at another example of a fused lasso. So in group lasso. So in this case, instead of adding the absolute value of every coordinate, now you decompose the coefficients into pre-specified groups, and then you want to figure out which groups of features, say which groups of the DNAs in terms of the different SNPs, and those you have prior knowledge that they all work together. So why don't we group their coefficients together? So you want to induce a kind of structure that's called a group sparsity. So if any group is non-zero, so we don't want to penalize individual components of that group. If it is 0, let's make all of them 0. If it is not 0, like let's play less of a restriction to that group. So this can be modeled using the group lasso type of penalty. And suppose you rewrite the problem in the same way that we deal with lasso, then you can solve the problem in very similar way. And notice that when you do this, the different groups actually splits. Therefore, in the second step, this allows you to parallelize the computation and solve for each group separately and then assemble the solutions. Okay, and the soft thresholding operator that applies to different groups is similar to the standard soft thresholding, but I guess it just differs in the sense that it is L2 and it groups everything together, right? So at the end of the day, if you start with X, you'll either make X entirely 0, or if the two norm of X is already within the threshold, then you just set everything to 0. Yeah, there's yeah, I forgot to mention this additional trick that can be used to improve the computation of every iteration of ADMM. So in both problems that we talk about here and here, we're solving actually a fixed linear system in every iteration. So the idea is that you don't have to resolve everything in every iteration, but rather you can you can compute some intermediate step so that later when you are only updating so we want to solve problems of this form, multiply with b for some vector b. So if we are only changing this b but not touching this linear system that we wanna solve, then you can keep track of the say the collective factors or eigen decomposition of this matrix. So later it becomes much easier to just directly apply those factors. For the collective decomposition, they decompose this matrix into upper triangular matrices, in which case you can invert each collective factors more easily by simply running Gaussian elimination. So that reduces the time complexity for solving the second iteration onwards to order p squared rather than order p cubed. Okay, so in practice, that p squared is as large as representing the matrix in the first place. So that can be like quite efficient and useful in practice. Of course, like if you have like sparse collective decomposition, you can further reduce this to the number of non-zero elements of the collective decomposition, but that's a tricky issue because even if X is sparse, then the collective decomposition might not be sparse. And if you prefer a sparse decomposition, then that's a problem that you need to solve in the first place. That I think remains one of the major open problems in numerical linear algebra. On the other hand, like the conjugate gradient solution that I proposed earlier allows you to get like linear convergence, which depends only on number of non-zero elements, while like getting only an approximate solution rather than the exact solution. Okay, so trade-offs. In practice, you could like try both and maybe use the collective decomposition as a fallback in case the conjugate gradient-based approach doesn't really like give you high enough numerical precision. Okay, so there are fancier applications of ADMM that can be used to solve problems related to matrices. So remember that at the first couple of lectures, when we talk about SDP and SDP relaxations, we talk about fan tokes, where the fan is like the late UCSB professor Key Fan's the elite mathematician that proved to date the most generalized form of a minimax theorem. So Fan's also known as like solving the principal component analysis by formulating it as an optimization problem, in particular a convex optimization problem. So we talk about the problem of sparse PCA. which add this additional condition that we want to find like sparse principal components rather than just the leading principal components in L2. So that is realized by formulating the convex optimization formulation of the PCA problem by adding this additional regularization term that penalizes the number of non-zero elements. And it's subject to a constraints. And again, this is a convex constraints in the form of a semi-definite ordering. So let's maybe think about how we can solve this problem using using ADMM. So notice that there are two bits that we need to deal with here that are somehow coupled with each other. So first, we want sparsity from here, and second, we want this matrix to be in Fantol, in the sense that we only want to get some kind of a rank K solution, but this is a convex relaxation of this rank K ball. So these two objectives might not always be compatible to each other. In particular, coming up with a prox operator to solve both of them simultaneously might be too difficult a task. Okay, so you can also like try other approaches, like solving this with the standard SDP solvers and with interior point methods, and those do not really scale up to practical cases where we want to apply this method to. Okay, notice that when do we want sparsity? Those are typically when we have really high dimensional observations, and in which case this is a P by P optimization problem. And it's huge when P, even if P is just 1,000, then you are dealing with a optimization problem with a median variable. Okay, so suppose we rewrite the original optimization in the standard form of like ADMM, like that, by introducing the dummy variable Z to split the two like direction of the regularization parameter. Then we can update the parameters using the standard ADMM, which involves the prox operator with respect to the indicator function to the Fantol. So this is Fantol projection. Okay, so it's already here. The Fantol projection. And the second step would be the standard soft thresholding operator, which is less interesting. So the cute observation here is that the Fantol projection can actually be solved with a single run of singular value decomposition. So you basically do SVD, and then you temper with eigenvalues. Well, by applying this operator that depends on this variable theta, which simply clipses in a way such that clip in a way such that there exists some theta parameter such that this becomes true. So you can do this by binary search over a bunch of theta. Okay, so that gives you a practical algorithm for implementing the Fantol projection, and ADMM in this case is actually the best algorithm that's available for this problem so far. And together with the statistical analysis that doing this, so this operator, this estimator, argmax, under certain statistical assumptions of how the data is generated, is actually a minimax optimal, right? So that solves the problem, not just optimization problem, but also the problem that motivates people to design this optimization problem to begin with. Okay, and the related problem is this sparse plus low rank decomposition. So sometimes we want to solve problem of the following form, and we M is our observation, so that could be the movie rating matrix, and from the literature of movie rating matrix. So maybe sometimes we get this projection operator that selects only those coordinates that we observe a rating for. So different users can rate only certain movies that they have watched, but not others. And the goal is to come up with a matrix that's low rank L, which captures the different factors of people's preferences on movies, and the sparse term, which measures the outliers. So there are people that are not typical, that are not captured by these low rank components. And maybe there are outliers that we want to just ignore. So this gives the so-called sparse PCA problem that has been extremely popular. So turns out that this is a standard ADMM form, and you can update the parameters by running the prox and then running the dual gradient ascent. And the two proximal operators are of the form of this is a singular value thresholding that we have learned before. Do a singular value decomposition and then shrink the singular values. And this, the standard coordinate-wise, the self-thresholding operator. Both can be implemented quite efficiently in practice. Here are some of the outcomes of this for foreground and background detection on the video surveillance. And you can see that like the solution actually gets a pretty good low rank components that's like maybe essentially rank 1 because it's like a static background. And all the moving components can be grouped together into this sparse component. So what if the original optimization problem is not decomposable by coordinates, but rather decomposable by blocks? Right? So X is not decomposable, but this F is in the summation form. So this is a standard type of distributed optimization problem where X represents a parameter that you are minimizing over. So maybe the parameter of the deep neural networks that you are training, and Fi correspond to the data that's available in only one of the servers, one of the nodes. So maybe you want to add more complexity to this to say that different Fi correspond to different entities that want to keep their own data private. And in this case, you have to design secure rules of solving this optimization problem that doesn't require, that doesn't leak the information about the original data. Okay, so so how to solve this problem using ADMM while still splitting the objective function as we had before. So this involves adding all kinds of dummy constraints where having an X in the middle, okay, and all the other Xi's, X1, X2, X3 are, so that's why this is called consensus ADMM. Instead of picking just one of the terms as a center, now we can like try to match everything to this additional parameter, like auxiliary parameter in the middle. And then the ADMM updates would naturally decompose into two groups. The one group is X, the other group is X1 to X to X, in this case to X4. Okay, so by these two groups, and then you can use the original ADMM and to solve this, and that gives you like a decomposable optimization problem in every iteration. So arguably, this is a more difficult part because it involves solving an optimization problem. What this is saying is that so in every iteration, so the different entity can just solve their own problem with their own data while getting like the central input that constructs the objective function. So this is in some sense the federated learning setting that had been very popular nowadays. That's at the intersection of machine learning and distributed optimization and distributed system. So maybe I guess, yeah, this is a wild thought, but thinking about blockchains, thinking about other like fancier things that people do in distributed system and its connection to ADMM might be something of interest if it hasn't been done. Okay, so I'm gonna skip this. yeah, so you can do this more generally when you have linear um, um, like affine function inside each fi by defining the yeah. So doing this kind of distributed optimization is one of the major focus of Stephen Boyd writing that survey paper. Okay, so again, I'm gonna skip this. So yeah, we are 8 minutes from 3, so I'm gonna leave the remainder part of the lecture on special decomposition of ADMM to be talked about on our Wednesday lecture. All right. Thank you guys for coming, and yeah, see you guys on Wednesday. Oh yeah, there's a question. Yeah, excellent question. So there's a question about what's the motivation of the augmented Lagrangian method. So maybe we can go back to that slide. So the motivation of augmented Lagrangian method is to solve a larger family of the problem using the same approach. So let's go back to it. Okay, so the augmented Lagrangian method is a reformulation of the original problem, but introducing the additional strong convexity parameter. So that like if you do not have this, then you are solving a problem which will end up giving you the sublinear convergence by doing the gradient ascending the dual, right? Since you don't have any additional assumption on F, then the dual will also do not have any additional conditions. It might not be differentiable. So even though you can solve the primal and construct the subgradient, but the subgradient descent has slow convergence rate. Suppose you use augmented Lagrangian by adding this term, then the objective function becomes like I guess strongly convex. And then the dual, on the other hand, will end up being strongly smooth, which says that the gradient descent converges convergence with a faster 1/k rate rather than 1/square root of k. Okay. Does it solve your problem? Great. Any other questions? All right. If not, I'll see you guys on Wednesday. Stay safe.